Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. This particular lecture we are going to see dynamic control. The last lecture itself I told, so next part would be coming on dynamic control. So we will go straight away to the dynamic model first, then we will see like what is inverse dynamics and how we can do dynamic control in joint space and task space. So in that sense we are trying to see how to you can say portray the dynamic model in a you can say block diagram approach. And then we will actually like move to the inverse dynamics, then we will actually like come to the dynamic control where the feedback element also come into a picture. So then we will actually like try to see what exactly the robot kinematics which we call differential kinematic model has given. So if you know the velocity, so we can actually like see by integrating this you can find the position. So in the sense what you can see by giving the q dot as the input, the kinematic block would give q as the output. Similarly, if you extend the dynamics block, so what would be the output? The q dot, but what would be the input? The q double dot. So in that case, so what one can actually like see, if I see my exact dynamic model, there is a gravity term is coming. So I can find the gravity term by taking q as the element, or you can say the state vector, then I can calculate. Similar way I can calculate the v of q comma q dot. So which is the other effect vectors. So where the q dot I can take and q I can take it from here. So similar way I can find the inertia matrix, because the inertia matrix is function of q, so I can do it. So now if I assume that the tau is known to me, which is the input, so then what I can do? I can do the forward dynamics, or if I know the control law of this tau, then I can do the controlled manner, right. So in the sense what we can do, we can find this q double dot from this particular equation. So this is the equation which we derived as a equation of motion, and that too like we have written in the you can say acceleration one side. So this is the equation we have derived. So now this is what we call the what you call robot dynamic model in block diagram approach. But if I want to write it in a simple form, so what I can see, the robotic system, so I can call robot. So robot will give q dot and q as the output by giving tau as the input. So this is the robot dynamic model, simply I can say in this form. So although this is the detailed one, but this particular case I can make it as a simple this way, okay. So this is what we are going to use hereafter. So for that only I have given this introduction. Let us move to the inverse dynamics. So what would be the inverse dynamics? What would be given to us? So the desired position, desired velocity, desired acceleration would be given to us. So in fact we will go for even fifth order polynomial or third order polynomial, we will be knowing this, right. So then what would be available to us? So would be available to us is actually like, so the inertia matrix based on the what you call the simple idea called the q dot decide and q decide is known, then we can actually like find this n of comma n of q decide minus q dot decide and m of q decide is known. So in that case what one can find? So the tau we need to find. The tau I can write as m of q decide into q double dot, okay, decide plus, so n of q decide comma, so q decide dot can be used. So this is what the inverse dynamic model. So this inverse dynamic model would be useful when there is no gravity involved. Whenever there is a gravity involved, it is very difficult to you can say use this as a open loop control, okay. That I will show you in the simulation time, probably next to next lecture we will be seeing that in detail, but right now we can see in this case. So for given this mu like m of q decide and n of q decide comma q dot decide is known, so we can actually like find what you call this tau. So this is what we call inverse dynamics. So even that can go even further end. So for example, this is the robot dynamic model, we can take it. So in that case, what we can see the controller. So in this case, the controller is actually like open loop control, that too like feed forward control. So if you have a block which is a trajectory planner is known, okay, so which will give the q double dot decide, q dot decide and q decide, then we can calculate tau in this form, right. So this is what we can see. So where I always actually like separate the, you can say, gravity term, so that we can actually like use gravity compensation later on. But as you know, so this would be actually like open loop control if your q double dot decide is actually like non-zero, and so q decide of 0 and q of 0 are same, then q decide dot equal to 0 and q dot also like 0. So then only this would be work as a proper control. Otherwise it's a simple inverse dynamics, but that will not follow that exact trajectory what you intended, okay. So then what would be the option? So obviously the option would be dynamic control. So the dynamic control means what we additionally we expect. So the actual position we will consider, take it as a feedback and put it in the loop and try to compensate. In the sense your tau, so tau would be function of so q and q decide, okay. So that additional term also would be coming. So but these are the cases which we are expecting. So in that case, what would be given? So q decide, so q dot decide, for example, if it is a set point, the q dot decide would be 0, okay. So similarly q double dot decide also would be 0, but for a tracking these all three would be given to us. So what additionally available? We assume that it's a feedback. So then what we assume that the actual joint position and actual joint velocity would be available. Further, if we are doing a model based control, so the m of q and n of q comma q dot also would be known. So in the sense I already said, we usually do a fused based control. So model based combined with the reactive paradigm, that is what we are trying to use. In the sense model based along with the feedback we can use it. So that would be feed forward come feedback control. So that is what one of the control which we are going to see in upcoming slides. So in the sense what we are trying to find out tau. For example, if we are trying to do it in a task space, so then the task space would be f, right. So then j transpose of q equal to f. So that also we can try to do it. So in that case what one can expect? So one can expect that the system is actually like a closed loop system is exponentially stable or asymptotically stable, in the sense where t tends to infinity. So q tilde and q dot tilde tends to 0. So what this? So this is the way. So in that sense the second order error dynamics supposed to be what you can say supposed to be stable. So in the sense we can actually like take it second order error dynamics in this form, where lambda 1 and lambda 2 are a positive constant. In this case it's a matrix, so we assume it's a positive constant, then we can see, so this would be fulfilling what you wanted. So in the sense we expand this equation, so we expand this q tilde double dot as q double dot decide minus q double dot. So this q double dot we know from the what you call equation of motion, and q double dot decide is actually like available from the trajectory planner. So in the sense this is what we can write it. So but this we know from the model, or you can say equation of motion. So this would be known. So we can equate these two. So what you will get? So you will get this final form. So here you can see the tau is the input. So we can rewrite and see what would be the tau. So tau would be coming in this way. Sorry, in this say in the sense this is actually like you can see the feed forward term. This is a feed forward term, and this is a feedback linearization, and this is the you can say feedback term. Here it is a simple PD control as such, right. So this is what we are actually like seeing it as a computed torque control in general in robotic community people call. So but we are trying to see that here. In addition to that, it need not to be all the time like this. Similarly, it need not to be this way. So even the feedback linearization need not to be come. We can make even motion based control, simple PD control or PID control can be used. So for that what we are actually like taking it. So before going to see that, so we can see like the same thing in a block diagram form. So you can see this is the control. So now we assume these two are actually like fed back. Okay. So now that feedback and the trajectory planner is giving the q dot desired and q desired. Okay. So then what we can see, like this is the simple PD control along with what you call gravity compensation. The same thing can be extended with the PID. So then you can see like I term is coming again. So then this is a simple what you call motion based control. So there is no, you can say feedback linearization or feed forward. So we see like what is your reference and trying to compare, and similarly like we are trying to compare this error. Okay. So this error actually like we are trying to use as a motion base. So further, if the system is in a spatial, so the gravity also need to be compensated, but most of the modern or even old manipulators all gravity balanced system. So either spring based or you can say the cable driven base, so or you can say some kind of electrical actuation base. So the gravity is already balanced. So in that case simple PD and you can say PID can be used. So even you take in the industry you can say ready manipulator, the PD control would be used. Already we know like why PD control is popular in robotic you can say manipulator community. So because the open loop system is actually like unstable, but this PD control make it stable. That is what the whole idea behind it. So in that sense we will go further. So how the computer torque control will come here we can see. So in the sense this is the controller. So now we are taking a feedback, and in addition to that you are taking the q double dot desired, we are taking a feed forward. In addition to that we are actually like trying to compensate these terms. Okay. So this is the computer torque control, and this is actually like we have seen in the joint space. So now we will see the same thing in the task space. So in that sense what we are trying to see, so we are trying to see the motion control in task space. So for that, so what we expected as a given, so the desired end effector position, velocity, acceleration all would be available. Further, so what would be available from the system side, so actual end effector position and actual joint position. So actual end effector velocity and actual joint velocities would be known explicitly. Further, we assume that the Jacobian matrix is important, so Jacobian matrix are available to us, and inertia matrix and what you call other effects all available to us. So then what would be the target to us? We need to find out what would be the end effector forces and moments, so that we can control the system in task space. So in that sense, so what we expect, the t tends to infinity, the mu tilde and mu tilde dot supposed to be 0, and we know like what is the syntax or what is the convention, we take mu tilde as mu desired minus mu. So in that sense we can actually like use what we know. So again we can come back to the second order error dynamics is actually like going to be a stable system where gamma 1 and gamma 2 are positive constants. So only thing, so earlier we have taken q tilde double dot and q tilde dot and q tilde. So here it is mu tilde double dot. So in that sense we can rewrite this equation. So we know mu double dot. So how we can write? So we can write mu dot as j of q into so q dot. So then the mu double dot is actually like j of q into q double dot plus j dot of q into q dot, right. So this can be used, or we can straight away use the direct relation. So then we can rewrite this here, and then mu double dot we can write it from this equation. Okay. So now these two we can equate, then you can see like the f would come as in this form, but we know certain relations. So that is what we are trying to use. So this is what the control input, but we know already these are the relations where the m of mu can be written in this form. Okay. So n of mu mu comma mu dot we can write it in this form, and tau we can write in the form of f. So now we substitute these all, we try to find out everything in a joint space because the actuator is connected at joint space. So we can actually like check it. So now if we substitute, you can see like the modified equation comes this way, right. So I already said it need not to be all the time feed forward term and all need to be come here, but we can actually like check it that. So this have a two option, Even you can actually like use j dot of q decide and to q decide dot, or we can use a simple feedback. So either way we can use it. So I am using as actual like feedback so that I no need to use it. Similarly, this also some people use. So j of q decide inverse, but we can use, you can say, actual system itself. So in the sense we will see first so PI and PI like a PED and PID. So then we will go to the computed velocity control or computed torque control in this case. So we see like this is the controller, okay. The controller required feedback and required actually like input from the trajectory planner. So then we can see if it is a PD control, we can use this way. But what happened, you need to give the input in task space. So we know like J is actually like so the tau is J transpose of so Q into F. So we calculate F this way, right. So then we can actually like add it this, so that it will come as tau, but we need to always compensate the gravity. But if you do in a real time manipulator, the gravity always compensated, but when you do a simulation, so then the gravity need to be compensated. So that's why we call it's a PD with gravity compensation control. Similarly, PID with gravity compensation control can be brought in. So now you can see like this is the I term which is added, so that the steady state error which ended in the PD control would be neglected, or you can say converged to 0 by introducing the I term, okay. So the same way we can extend to the computer torque control. So you can see this is the system and this is the controller. We take a feedback and we give like 3 inputs from the trajectory planner. Both you can say earlier we give only desired position and velocity, now desired acceleration also we added. So then what happened, this is the control law which comes to us, okay. So this is the computed torque control. Why this name has come computed torque control? Because we are computing the torque. So most of the you can say olden days manipulator all are actually like rotary actuator base. So that's why the torque need to be calculated. So that too like we use a direct drive motors. So in the sense if you compute the torque based on you can say model and the feedback, then we can compensate directly on the actuator level. So that's why it is called computed torque control. So it need not to be called a computed force control, because olden days so it was all rotary actuator, that's why the computed torque has come as the keyword. So now the keyword we cannot change, so that's why we are also using computed torque control. Even your manipulator have a you can say prismatic joint inside, still we call computed torque control. I hope you are actually like get some idea about what is dynamic control and what are the way it can be you can say evolve, and how the computed torque control have come. So what basis it has come, the second order error dynamics converges to 0. Now the choice of you can say gamma 1 and gamma 2 we can actually take it as per what you call your second order system dynamics. You want probably a critically damped system, then we can take K1 as you can say 2 omega and K2 as actually like omega squared. So where omega is actually like your output frequency, anyhow it is actually like critically damped, so it won't actually like go any oscillation, but this is the way we can actually like take it. So now this omega is related with your you can say rise time, so we can actually like make it that way. So then the K1 and K2 will come as per that way, so that the K1 K2 even relate to lambda you can say gamma 1 and gamma 2, or you can say lambda 1 and lambda 2, okay. So now I hope you are actually like getting some kind of idea. So but if you have a manipulator which is gravity balance, even simple PD control is quite enough, but you want to go for very accurate precise position following and all, then you have to go for modern control. Even then the model based control may be having uncertainty, I already said. So then we have to go for robust or adaptive control. Those things we will see in at the end. Right now we close here with dynamic control. The next lecture we are going to call like dual loop or double loop control, where kinematic control and dynamic control we are going to combine. So most of the control community people call it's a backstepping. So that is what we are going to see in the upcoming lecture. Until then, see you, bye, take care.